Hi there, welcome to your lesson on the tangent function. Let's get rolling. As we've been doing in our trigonometry unit here, I'd like to begin with a little flashback, looking back at the journey we've taken through trigonometric functions so far. So we began with the key concept of a unit circle, and within that unit circle, a right triangle, and a unit circle having a radius of 1. Producing these lengths of these sides of the right triangle, where this side here is sine theta and this side here is cos theta. And that represents the y value of a coordinate on the unit circle, whereas this represents the x value. We also know that tangent of an angle is the quotient of sine over cosine. We also learned the Pythagorean theorem within this triangle. If we apply it, we have sine squared theta plus cos squared theta equals 1. And that leads to what is called the trigonometric identity, one of our key identities or rules in these unit circle triangles. At all kinds of angles, we know that there's any angle is possible in the unit circle, but there are certain key angles like 30, 45, 60, and they produce these side lengths with a very specific proportions. We then placed these special angles along the unit circle and named them in degrees and radians, and then that allowed us to label the location of each point of those key points along the unit circle using the x and y values, or the values from those special right triangles. After that, we said, well, let's graph each thing. If sine represents all the y values, for example here, sine represents all these y values, the second part of each coordinate. So as we spin around the circle, what are all the y values? Well, we know in the beginning, when we start at an angle of 0, the y value is 0. And then we're imagine spinning around the unit circle, angle gets bigger, y value gets bigger. All right, and that leads us to the sine curve, where we see when y values go up as the angles increase, then down, and then up again, until we get to 360. For example, when we go 90, 1/4 of the way around the unit circle, the y value has a value of 1, right? On and on. We also did the same thing for the cosine curve, and it turns out it looks very similar to the sine curve. It's also a wave, and it looks like this. However, cosine begins at 1, because when we have no angle on the unit circle, we are at an x value of 1. All right, that's what we've seen. So now naturally we're thinking, well, what about tangent? What about the tangent function? What does the graph of this one look like? Let's take a look. So what happens to tangent values as we move around the unit circle? Let's check. We know again that tangent is sine over cosine. So let's begin with an angle of 30 degrees. Here's our unit circle. Here's an angle of 30 degrees. We know to find tangent, we're going to do sine over cosine. In this case, sine value, this distance here is 1/2. Cosine value is √3/2. So we're going to say tangent is sine over cosine. When you divide those values, this y value by this x value, you get 0.58. Okay, so tangent at 30 degrees is 0.58. Let's try another angle. Let's try 45 degrees. So here's 45 degrees, it goes to here. When we have a 45-degree triangle, we know it's 45, 45, 90. That means both the x and y values here are the same, √2/2 and √2/2. Therefore, when we do the tangent, we have √2/2 divided by √2/2. And that means we have a value of 1. So as tangent went to 45, the value of tangent became 1. Remember, for sine and cosine, the highest value we can have is 1. But in this case, we seem to see that as we keep going here, maybe we'll have a tangent value greater than 1. So let's try another angle. How about 89 degrees? Whoa, 89 degrees is going to bring us really close to 90. So it's going to make this tiny little skinny triangle. And in that triangle, it's not one of our special ones with 30, 60, 90. And it's not one of our special triangles, so we cannot rely on our 30, 60, 90 or our 45, 45, 90 triangles, but we can still calculate this, right? Because tangent is still sine over cosine. So tangent of 89 will be sine of 89 over cosine of 89. In this case, we'll need our calculator. We can find sine of 89 is 0.9998 and cosine of 89 is 0.018. That makes sense because look, as we get closer to 90, the y value becomes a number very close to 1, because at 90 the y value will be 1. So notice the y value is very close to 1. But what happens to x value? Well, this triangle became so narrow that the x value right there, the x value is barely away from 0, right? It's a tiny value. 1 would be here, but the x value is here. So it's 0.018, very small. So divide that number and you get 55.5. So the tangent value has surpassed 1 by a lot. It's actually become quite big. But let's go even further. What if we went even further? What about an angle that's even closer to 90 than 89, extremely close to 90? So we know as you get closer to 90, the sine value becomes nearly 1. So imagine having a number that basically is 1. But on the bottom, the x value becomes a tiny value, even smaller than what we saw over here. You could say it's 0.0000001. So you have a number that's almost 1 divided by a teeny number. And the result of that is a huge number. So notice how tangent was growing much more quickly here. It's going to become even bigger as we get closer and closer to 90. So what's going on graphically? Let's take a look. So we're going to graph tangent of theta. First of all, when the angle is 0, our value is 0. Why? Because when the angle is 0, our sine value is 0. We haven't raised that point at all from the axis yet. So y value is 0, x value is 1, so 0 over 1 is 0. Okay, we saw what happens at pi over 6, which is 30 degrees. We had a value of 0.58. We also checked the value at 45 degrees, which is pi over 4, and we found out that one was 1 exactly, because we had root 2 over 2 divided by root 2 over 2. Then we checked, we didn't check 60, but the value of 60 would be 1.73. And then we took 89. I don't have 89 on here, but I'm putting something close to 89. But what we see is the tangent value is rising. But what happens when we get to 90? Think about what happens at 90. What would the tangent value be? At 90, our y value is 1, but our x value is 0. So tangent would be 1 over 0. And that's undefined. We cannot divide by 0. So what happens is we have an asymptote. Whenever we have undefined things in mathematics, graphically, it is an asymptote. So you can see the tangent values are getting close to there. And we saw when we took an angle really close to 90, the tangent value became huge. And that's why this is rising up exponentially. It's following and going up to the limit of the asymptote, becoming a huge number. Now, my next question for you. Where will be the next point, or what would be the next angle where the tangent value will be 0? Well, that next angle will be 180 degrees. Why? Okay, imagine going halfway around the unit circle. Now you've arrived at a location where the x value is -1, but the y value is 0. So our tangent value will be 0 over -1, which is 0 again. Okay, next question. Where will be the next asymptote? We had one at 90, and we talked about why that happened. Where will be the next asymptote? What angle? Well, the next asymptote will be at 270. Let's think about why that happens. 270 is 3/4 of the way around the circle. So now you're at that very bottom point on the unit circle, where the y value again is -1, but the x value is 0. So we end up with -1 over 0 for tangent. We cannot divide by 0. There's our next asymptote. So we see a pattern emerging here. And the pattern is this. Tangent graphs will look like this. It'll be a repeated curve that looks like this. Okay, with these asymptotes where it's undefined, and also all these points where it has a value of 0. We didn't talk about the negative side here. Let's talk about that for a moment. Why is there a negative portion on each part here? Because, for example, when you are, let's see, let's go with this one. We know it begins at 0, but if you, no, let's do this one. When you do an angle less, this is an angle of 180. So as you're approaching 180, okay, so after 90 degrees, this was 90 degrees, and this is 180. What's happening between there? Let's say we do 120 degrees. So imagine that in your mind's eye, 120 degrees on a unit circle. We have a negative x value and a positive y value. So that means you will get a negative answer, right? Negative divided by positive. So that's why we have these negative bits as well. So there is your graph of tangent theta, or tangent of x. What does this graphic show? My tan lines are showing. Well, there's the tan lines, the curves from the tan graph. And tan lines, well, you may have gone to the beach at some time in your life, and maybe you had a strap or an article of clothing, and you had these lines, and your tan was ruined. So there are some tan lines. There's some math humor for you. This is about as funny as mathematicians can get. Okay, so tangent, let's recap. There are definitely some similarities between the sine and cosine curves and the tan curve. All these curves, the ones we've looked at before, sine and cosine and tan, are called periodic because there's a repeating pattern. And that's what we see going on here as well. The transformations, horizontal, vertical stretches, reflections, translations, all these rules apply. But for the tangent, the period is 180 or pi radians instead of 360. So a sine and cosine graph had a period of 360. That means it takes 360 degrees to complete one full wave. But here we can see it takes only from negative 90 to 90, which is 180 degrees to complete one of these cycles. So the period is 180. All right, and tangent graphs have no amplitude because there's no upper point. Sine and cosine have that upper point, lower point. We could say there's an amplitude or a height to the wave, but these ones, there's no amplitude. All right, let's go on with that. So here's the exercises that in our textbook we look at these problems. Here's a basic tan graph, and we're going to try a few of these together. Let's try 1A. So we have 1A, it says tangent of 2 theta. So these ones are all about practicing what effect would our transformations have on the tangent graph. And we dealt with transformations in the last lesson. We looked at them in detail with sine and cosine. So now remind yourself, what does this 2 do? What does that affect on a graph? In terms of transformations, what does putting a 2 here with the x values do to the graph? So explain how this will change. All right, here's how it will change. That 2 there is a horizontal dilation. And remember with dilations, the number we see, the effect on the graph is the reciprocal of what we see. So we see a 2, so the effect is that the graph will become compressed by half. So every x value will be half of what it was. So if the asymptotes were once at pi over 2, well now they're at half of that, which is pi over 4. All right, and then the jump between asymptotes, instead of being 180 degrees, now the period is 90 degrees. So from pi over 4 to 3 pi over 4 is 90 degrees, and so on and so on. So basically the whole graph got compressed horizontally. All right, next one, let's try 1C. It looks like this. So now we see the tan part here is unchanged, but there's this -1 in front. So what effect would that have on the graph? All right, that effect is that the whole graph moves down by 1 unit. This is a vertical translation, right? The whole graph moves down 1. So notice the normal tan graph intersects at these points here at 0. Well, if the whole graph shifted down 1, notice those middle points, the middle points of the curves are now at -1. The asymptotes remain where they would be here. Okay, let's try 1F. Okay, so I see a 1 here, and I see this here. So what effect do those two things have? What do they do to our tan graph? How do they transform it? All right, so the 1 again is a vertical shift, a vertical translation, goes up 1 unit. So we can see now these points where we're intersecting the axis are now here at 1. And then this tells us we have done a horizontal translation. And remember that one, we always do the opposite move that we see. It says plus 3 pi over 4, so we've moved everything minus 3 pi over 4. Okay, so minus 3 pi over 4. We began with an asymptote at 90 degrees. Minus 3 pi over 4 would be minus 135 degrees, so we're at -45 degrees. So this asymptote moves to -45, which is right here, -pi over 4. These are a little tricky. You might need to pause and try some things on your own, but just reminding you of the transformations. Okay, so now let's look at something different. Let's say we had this equation and you had to solve it. So one way we've solved trig equations is to graph them. All right, so if we can graph this as one function, so for example, we're going to do this on our calculator. You have one function, which is tan x, and another function, so you enter both in your calculator, 1 minus x. So you have this thing and this thing. You graph them together and you see where they intersect. So try that now. It might be tricky. You might end up with a graph like this, but if your graph doesn't look like that, take a look at what our window settings should be here. So this was set at -2 pi, and this is positive 2 pi. So set your window x values, max, min, like that. Your y values can be, I don't know, it looks like it's -8 here and 8. So let's take a look. So where are the intersections? Well, first of all, we're looking in the domain of -2 pi to 2 pi. So within that domain, we have a few intersections. Here's one. Find one of the other ones. What should this one be? All right, now let's try some problems like that. Try this one here. Solve this on this domain. And check your answer here. I graphed it. I found 2 answers within that domain. One more. Try this one here, 2D. and now check your answer. Hey, that was a great one. It was a parabola and a tan curve, and they meet 3 times.